Okay, can you see the slides?
Yeah, do you want to try the full screen?
Yep.
Yeah, perfect. And we can
Okay,
also
good.
see the pointer. Okay, great. So we'll start immediately again. Our second speaker today is Ricardo Monteiro, who will tell us about superstring loop amplitudes from the field theory limit.
Okay, thank you for the invitation. This is work done with Yvonne, who's chairing this session, and also with my former student, Ricardo Startenschau. And what we try to do is to learn about superstring loop amplitudes using the field theory limit. Now, typically you think about it the other way around. So let's consider the scattering of massless external states. And then the field theory limit of the string theory amplitude is when you send alpha prime to 0, then the massive modes decouple. And well, here you have string perturbation theory. So at each order, you consider a correlator on a Riemann surface of a particular genus, and then you also integrate that correlator over the moduli space of the surface. And this corresponds then to tree level, one loop, etc. for the field theory. Historically, this has been a hugely powerful tool to look at field theory. In particular, the first one loop results in the widely popular theory n equals 4 super Yang-Mills and the also popular theory n equals 8 supergravity were obtained in this way from a one loop superstring calculation. Then you obtain these boxes that many people here are familiar with. And there are other lessons, for instance, the double copy. Basically because at each order in perturbation theory, there's a single diagram. And although it's, well, it's quite complicated in many ways, you can do basically like complex analysis on the world sheets to figure out some nice algebraic properties of the amplitudes. Okay, and what we'll try to do here is actually precisely the other way around of this, but we'll go up to 3 loops. So given the knowledge of some result like this, we want to go in this direction. Notice that here, I told you about these theories, which are 4-dimensional, indeed in 10 dimensions due to UV divergence. Yeah, you can consider the amplitudes, but you can consider the loop integrands, and that's what we'll look at. That's enough for us. And in the examples that we will consider, actually the dimensional oxidation as opposed to reduction is straightforward. Okay, so let's think about the relation between these string theory amplitudes and field theory amplitudes at tree level. We'll be considering here closed strings. So there's an infinite power of massive states. We consider an integral over the moduli space of the sphere. So the answer depends on alpha prime. And we have here the Kobe-Nielsen factor, and there's some leftover correlator for depending on the left moving sigma and the right moving sigma bar. Now, many of you will be familiar with the fact that there's a very similar formalism directly for field theory, applicable typically to field theories of massless particles. At least that's what I'll be thinking about here. That's a CHY formalism based on the scattering equations. And in fact, there is a world sheet model known as ambitwister strings, which is kind of a cousin of string theory, but that actually describes particle theories disguised as string theory. So this is so there's a finite massless spectrum, and this is the form of the amplitudes. There's an integral over the moduli space, but it's actually completely localized by the solutions to the scattering equations. So these are some critical points in moduli space. Obtain solutions to these equations. In these equations, you give them an Einstein variable, and you solve for some complex numbers, which you should think of as points on the sphere. And there is also here, in a slightly different way from string theory, but quite closely related, also some kind of splitting between two factors. it is not trivial to see that this type of expression can arise from the vanishing alpha prime limit of this kind of expression, because this is a chiral expression, only depends on, say, the left movers. But it is possible, and there is a very important observation for this talk, which is that if you make a wise choice of these objects, which I'll call the half integrands, so half moduli space integrands, then you can actually use them in both. And there is also something interesting about large alpha prime limit, which I will not discuss here. Okay, before I tell you how to choose this, let me just remark that the splitting here between left movers and right movers is precisely the origin, the string theory origin of the double copy. So this goes back to the work of KLT. So suppose you consider the scattering of factorizable asymptotic states. So you have closed string states which are factorizable, let's say of this type for a polarization tensor, and then they look like the product of open string states for the left polarizations and the right polarizations. What is not obvious, and these people showed how to do it, was how to factorize also the expressions for the amplitudes in this sense here, these half integrands. So basically there's a two-dimensional integration here over the one-line space of the sphere, and you can disentangle this with the residue arguments into two integrations over the boundary of disks, which correspond then to open string amplitudes. In the lower energy limits, you get gravity as a double copy of gauge theory. So this is just schematic. Right, and you can look at these Kelty relations in the limits when alpha prime vanishes. There is an alternative point of view for the double copy, which has been extremely useful, especially at loop level, but also at true level in a variety of theories. Just brings it into a more general framework, which is the BCJ double copy. So it's based on the color kinematics duality. So let's start with a gauge theory amplitudes. Well, you have to express the color. You choose to express it in terms of color factors. There's some FABCs which are chained together. This has the form of a cubic diagram, the color structure. So then you can have propagators 1 over p squared per internal line of these diagrams. And then you have some kinematic numerators that will give you the right amplitudes. Now, these are not uniquely determined because there are linear relations between the color factors. They are the Jacobi relations of the Lie algebra of the gauge group. But what these people showed is that you can actually choose them to satisfy the same identities as the color factors. And if you can do that, then you can just obtain for free the gravity amplitude for states like this, where you have two copies of these numerators. And these two copies should be thought of as being precisely related to, say, having two copies here or two copies here. So let's say for the CHY integrals for gravity, then these half integrands, one will depend on the polarizations epsilon, the other one on the epsilon tilde. And this, once you perform the integral, this gives you this. So this integral is actually a multidimensional residue integral. So it's fully localized, as I mentioned. Now, what is a good choice for these half integrands? Well, you can write it down using the BCJ numerators. So you write some BCJ numerators over a so-called particular factor, where you have a cyclic chain of some sigma ij's. And yeah, you consider here in this sum all the diagrams of this type. So for all the permutations of this one, so these are half ladder diagrams, you could choose other particles to stay here. The result of the sum is the same. So if you input here the numerators for these trivalent diagrams, then how doing this expression appear the numerators for the other diagrams? Well, they are related by Jacobi relations. And these are the master diagrams in the sense that they know about all the others. It's a choice of master diagrams. Many of you will know that you can also express this object for the CHY integral as a CHY Pfaffian. And the two expressions are equivalent on the support of the scattering equations, but not off that support. And indeed, you cannot use then this expression and expect it to work for the string. Okay, so this was tree level. So what about loop level? Well, the BCJ story extends to loop level, or is proposed to extend to loop level for the loop integrands. So there you have, again, some trivalent diagrams with some color factors, propagators, and numerators. There are some internal symmetry factors. And yeah, if you find BCJ numerators, then you get gravity as a double copy of such numerators. If you can't quite find them, there's also a way around it. The first very non-trivial example of this was the 3-loop 4-point amplitude in n equals 8 supergravity. Well, Super-Yang-Mills double copying to supergravity. And this is actually will be our main result will be related to this amplitude. And well, the numerators, they have some permutation invariant factor that knows about the particular states, their polarizations or fermionic states or whatever, which is just imposed by supersymmetry. And then that multiplies a polynomial of the Mandelstam variables, STU, and of k dot L's, where the L's are the loop momentum. And these are the diagrams appearing at 3 loops. Right, so this is for the diagrammatic perspective on the field theory. What about string theory? Well, at loop level, you look at higher genus surfaces. Let me give here the example of genus 2. So actually at genus G, there exist G holomorphic differentials on a Riemann surface. And so at genus 2, there are two linearly independent ones. Now what you do is to pick a homology basis of cycles. So there's some A1 cycle here. I don't know if you can see it, A2 cycle, some B1 cycle, some B2 cycle. You can do different choices of cycles. They are related to, well, under some intersection rules, they are related by modular transformations. And well, you choose your particular holomorphic differentials, so the particular linear combinations, such that they normalize the A periods of these differentials. Then the B periods give you the period matrix, which turns out to be symmetric. So there are 3 modular parameters, which can also be described in terms of these QIJs. Now, there is an important degeneration limit of this, which is the maximal non-separating degeneration. So basically, you degenerate, you pinch these 2 A cycles, and you get a binodal sphere. So there are 2 nodes, each node is a pair of identified points. So this then in the limit has genus 0, but has these nodes. You achieve these limits by taking the diagonal elements of the period matrix to I infinity, or these Q's to 0. And these holomorphic differentials, well, they're no longer holomorphic because that's not allowed. At genus 0, they acquire poles precisely, each one of them at these nodal points. And there's been a line of work that has shown that just like this is relevant for string theory, this is actually directly relevant for field theory. So let me tell you a bit about that, starting with string theory. And so I'll be telling you, I'll showing you some expressions that have been shown to hold at least up to 2 loops by direct calculation, or at least 2 low points. And we'll be focusing on a type 2 superstring up to 2 loops, and indeed 3 loops, at least for a low number of points. It doesn't matter if it's type 2A or type 2B for the things that I'm going to say. And well, you do an integral over the moduli space for genus G n marked points. So this is for scattering of n particles. There's an integration over the modular parameters. There are the moduli associated to the marked points for the external particles. I'm actually going to include them here inside these half integrands because that's actually the correct geometric way to think about it. And so you have something very similar to what we had before, these 2 half integrands, I and I bar. So these will depend on the Z's and on the Z bars. And this is a chiral splitting representation. So in order to make a neat separation between these Zs and Z bars, this loop momentum is introduced. So it has interpretation of the loop momentum when you take the field theory limits. And there is an associated Kobe-Nielsen factor at loop level. This is the prime form, which is just Zi minus Zj at tree level. The analogous story obtained via the Amplitudes string is a formula on the nodal sphere. So there's also a kind of formula at higher genus, but I won't be discussing that. And here you get a formula for the loop integrands. So you get some half integrands, but now this is a CHY type formula on the sphere, but with n plus 2g marked points, n for the external particles and 2g for the pair of points for each node. So there are g nodes. And there are then, there is a corresponding number of scattering equations. Okay, so before at tree level, you could just identify these ones if you chose them in a smart way. So yeah, let me just say that in string theory, you have this freedom to choose because of integration by parts identities, because you're integrating this. And in field theory, on the support of the scattering equations, so you can write different expressions that are equivalent on the support of the scattering equations. But so with the correct choice at tree level, you could choose them to be the same. But here, you can't do that yet because this has also form degree in the loop punctures, not just the external particle punctures. But there is a very simple relation between them that can be observed, the two loops, where there's a differential form, which is a Jacobian, which then carries the weights of the nodal punctures. So this is a Jacobian related to changing the coordinates on moduli space from this period matrix to these nodal points in the degeneration limits. So this half integrands is then the stringy one taken in the degeneration limits and then with this Jacobian. Right. So given this observation, what kind of strategy can we design to tackle loop superstring amplitudes? Well, we can start with a field theory result, translate it to some different way of expressing field theory, and then try to uplift it to string theory. In this first step, we consider the supergravity loop integrands. So we know the BCJ numerators. That's actually the example I showed you before of this at 3 loops, which is a result that is from 2010. Then you can translate that using this worldsheet BCJ map, similar to the one at tree level, and obtain some expression which you interpret as being the degeneration limits of something coming from higher genus. So now we are at this stage, and now in the last step, we want to uplift it. We want to find the object at higher genus whose degeneration is this object. And well, that's in principle quite difficult, but modeling variance is a very strong constraint. So the idea is going to be to bootstrap these objects. So it must be a modular form of weight g-4 in order to make sense in the moduli space integral for string theory. It carries differential form degree in the external particle punctures, as I mentioned. So what we will do is just to write down a linear combination of such objects, all that we know about, and then fix the coefficients in that linear combination by matching to the degeneration limits. Okay, so there is no complete classification of these objects, so we'll just try known ones. I'll just mention it very quickly. There's these holomorphic abelian differentials. With them, you can form some, at any genus, a modular form of weight -1, which depends on G marked points in this way. There are also third kind abelian differentials that have a canonical definition. So these ones are not holomorphic, but instead have residues 1 and -1 at 2 marked points, Zi and Zj, which I represent here in these indices. And there are also some sums over spin structures, which are familiar from the RNS string, from the correlators of the worldsheet fermions. So these Zego kernels are the propagator on the on a genus G surface of worldsheet fermions with spin structure delta. So the spin structures label the periodicity or anti-periodicity conditions of the worldsheet fermions on the cycles of your Riemann surface. And this sum is like a democratic sum over all of them with a certain chiral measure, which can be a quite non-trivial objects. Okay, so let me just give the example of two loops. Just because it's just easier in that case to write the expressions, and then I'll just flash you the 3-loop result. So we will be considering 4-point amplitudes. These are quite simple in the sense that, so they have the simplicity that all the information about the massless external states, about which particular state it is actually carried by an overall factor, which at least in type 2b, you can just split into 2 factors, which you can absorb in each of the half integrands, but you can just then forget about this factor in general. So it's taken care of. Then you look at the supergravity loop integrand in BCJ form. This is given by some double boxes, planar and non-planar. Here's a planar one. And you read off the numerators of half-ladder diagrams, of tree-like half-ladder diagrams like these, just by opening up these loops. And these numerators are very simple. Apart from this permutation symmetric factor, they're just some Mandelstam variables. So at 2 loops, this is very simple. Then, so you know the right-hand side of this worldsheet BCJ map. This Jacobian is very simple to calculate. So you know this object in the degeneration limits. And at 2 loops, you can easily uplift it to genus 2. There's just a very natural object that you can use, this delta G, in this case delta 2, which has modular weight -1. So the answer here is modular weight -2, as it should. And this reproduces the result known from long ago, 2005, the RNS computations of Docker and Fong, and the pure spinor computation of Berkowitz. Now, the interesting part is the 3-loop results. Now, because of the time and how much more complicated it is, I won't describe it here in detail, but it has the same overall factor. It is now linear in the loop momentum, so it does depend on the loop momentum because the BCJ numerators are also linear in loop momentum. And so via this worldsheet BCJ map, it imports that. And okay, this is the answer. It's, well, the objects that I mentioned before appear there. I'm not going to say anything about it in the time we have. This chiral measure is quite non-trivial. It was proposed by Cacciatore et al. Long ago, based on work also by Docker and Fong. There's some special role here, the hyperelliptic sector within the genus 3 family. And this answer satisfies some consistency conditions related to monodromy, how you relate the punctures to your choice of homology cycles. There's been previous work at 3 loops using pure spinners for the lower energy limits. So in the leading lower energy contribution by Gomez and Mafra, which match the prediction from S-duality. So by some relation to the non-perturbative sector by Green and Van Hoof. And yeah, this should match that, that result, we hope. So this is in progress. And let me just say that this first part was reproduced independently. So this part with loop momentum was reproduced independently by these people. Okay, so yeah, we think this is a very solid conjecture. This is what I had to tell you. Is a new idea for how to import the huge progress that has occurred for studying field theory amplitudes into the very hard topic of superstring amplitudes. We gave here a very concrete application of these methods at 3 loops. Future directions, well, I guess it's a conjecture. To be nice to have more checks. I've only talked about the moduli space integrants. So a whole different story and very complicated is the integration, which is typically done only to the lowest alpha prime orders. And just to give you an idea of why we need different methods to look at superstring amplitudes, well, the 3 level and 1 loop results go back to the origin of the type 2 superstring in 82, 2 loops 2005, 3 loops maybe 2021, and yeah, it would be nice. It would be nice if this kind of idea can push this forward. And finally, well, is there some deeper lesson here for string theory hidden in this connection? So, well, that's what I had to tell you. Thank you.
Thank you, Ricardo, for a very nice talk. Any questions? We have time for maybe 1 or 2 brief questions.
I have a question from the opposite direction. So if you use the string amplitude to calculate the field theory amplitude at 3 loops, so if you had the result wanted to go in the opposite direction, from what I understand, you get the representation of the integrand using these linearized propagators, right? In at least the way how you did it at 2 loops. So in the same setup, you would get.
Yeah. So yeah, this representation of loop integrands indeed has these linearized propagators.
Now, my question is like general here. So is it guaranteed, or is there a procedure how to back to the quadratic, like in the general case? So even at 3 loops or beyond.
So actually here I used some BCJ numerators, and they were obtained for quadratic propagators. But in this case, it's actually trivial to relate them. Because the numerators, well, they only depend on things like L.K, and then this is very easy to go from one representation to the other representation. Now, you are asking if that introduces some subtlety in going from here to here. So first of all, we're not going from here to here. We're not going from this whole formula to this whole formula. We are just recognizing that, just like in other contexts of scattering amplitudes that we looked at, there are objects that can be imported from one theory to another theory. And yeah, we see no obstruction to that up to 2 loops, and we don't expect one at 3 loops. Yeah, but it would be nice, of course, to look at this, at approaching this directly, and indeed, people have been doing that, and that's why I believe this is the approach that has been taken by these people. I may be wrong, they may correct me.
Okay, so the procedure to get from superstrings to field theory, this is based on tropical geometry. I think the key paper, at least in recent days, is by Piotr Turkin from 2013, who explained quite beautifully how the differential forms degenerate from generic pointed moduli space to this boundary where the field theory answer is sitting. And here, to be honest, when we constructed this the coefficient of the loop momentum, we were looking at bits and pieces of the pure spinor result from Carlos and Humberto and matched with suitable bosonic components like T8 tensor times suitable combinations of momenta.
Yeah, so actually, I should have mentioned this very important paper by Piotr. Here, somehow, this BCJ/CHY structure is somehow doing this, somehow doing this decomposition into diagrams in an automatic way, which maybe still needs to be completely understood at loop level.
Okay, maybe in view of time, let me postpone all further questions to the Slack channel. Ricardo, I think you had another announcement you wanted to mention briefly.
Yeah, so I would just like to say something about about SageX. So many people here are familiar with this training network that has funded 15 PhD students, 3 of whom are actually speaking in this meeting. And these students in their SageX activities have done a lot of work on outreach, including an amazing online exhibition, which is finished, and you can reach it from the SageX website. When I upload the slides, I will add some hyperlinks. So it's an exhibition about sketching amplitudes. You can see here gravity, Feynman diagrams, beyond Feynman diagrams, etc. This is some version of the amplitude that you figure that you may have seen. And they've also made a 1-hour film on their experience of being a PhD student. And so the trailer is on YouTube, and in 6 months, the whole movie will be available. If you want to see it before and show it to your students, for instance, you can ask me or other people in SageX. Yeah, it's a very charming film, which may be useful for your students and may take you back to your own days as a PhD student. Okay, thank you.
Great, let's thank Ricardo again.